Hey Dr. Storr, my name's Phillip Hensley, and I'm a senior over at Tarleton State, and I chose problem number 17 from chapter 3 to do for this legacy project. And in order to solve that problem, you have to have an understanding of separation of variables, which is a method to solve partial differential equations. Chapter 3 gives us Laplace's equation in 2 dimensions. And this is an example of a partial differential equation because it has dependency on both x coordinates and y coordinates. And so the method of separation of variables will allow us to solve that. So in order to give a background to separation of variables, I'm basically going to solve Laplace's equation, 2-dimensional version in Cartesian coordinates. And the first step in doing that is assuming that the solution to your differential equation has a product form where the multiplicands are a function dependent fully on an x and a function that is fully dependent on y. And you plug the solution back into Laplace's equation up here, and then you do some simple manipulation to it. And then through some simple algebra, we're able to split up the x-dependent terms from the y-dependent terms. And this relationship from the previous slide right here is only true if both of these terms are constant. So what we do is we set each term equal to a constant where the sum of those constants is 0. And one of these constants has to be positive and the other has to be negative, and really it just depends on the setup of your problem which one you choose to be positive and to be negative. For the purposes of this derivation, we choose the positive constant to be the x1, we call it k squared, and then we choose the y1 to be the negative one, we call it negative k squared. And so the differential equations of this form, we derive the solutions back in our ordinary differential equations classes. And so we have x dependent on exponential functions and y dependent on sinusoids. And if we multiply these two functions together, we have the resulting potential, this is exactly how the book solved the Cartesian version of the problem. And then if you're given some initial conditions or boundary conditions, you can solve for each of these individual constants, a, b, c, and d, and you can get the exact solution for your problem. Problem 3.17 asks us to reference examples 3.6, 3.7, and 3.9. And all of these problems were solved using the spherical solution to Laplace's equation, which I just quoted directly from the book right here. And this whole term are the associated Legendre polynomials based on the value of L. Part A of problem 17 asks us to find the potential inside and outside of a sphere if the outside of the sphere is held at a constant potential V0, and it asks us to use the resulting equations from example 3.6 and 3.7, which I listed right here, and these A sub L's and B sub L's correspond to the A sub L and B sub L within the summation. Now in our problem we're given that V0 is a constant rather than in the slide it says it has a dependence on theta. So since we know it's constant, we're allowed to pull it out of the integral because the integral only depends on the theta term. And the Legendre polynomial for L equals 0 is equal to 1, so we can multiply our equation technically by 1 and slide this p sub 0 cosine theta into our integral. Applying the orthogonality rules from equation 3.68 in the book, we have that this entire integral right here evaluates to 0, which means this entire a sub L expression is equal to 0 for any value of L that's not equal to 0. But in the case of L equals 0, we have that the integral evaluates to 2 divided by 2L plus 1, and since L is 0, it evaluates to 2. So doing some simple algebra, we have 2 times v sub naught over 2 r to the 0, which just simplifies out to v naught. So we have that a naught equals v naught. And now that we've solved for a sub 0, we can plug it back into our original voltage equation, and both of these terms evaluate to 1. So we're left with the voltage is equal to a sub 0, which we previously found to be v naught. So at any point inside the sphere, we have a constant voltage of v naught. And then next we're asked to find the potential outside the sphere, and we'll be using the results from example 3.7. And again, we have a constant v naught, so this v naught of theta will come out of the integral again. And then we follow the same orthogonality conditions as in the previous slide, and the integrand will evaluate to 2 for L values that are equal to 0, and it will evaluate to 0 for L that is not equal to 0. So then we're left with this original voltage equation. We just plug it in again. This we just found to be v naught r up here, and then this value is r, and this is 1. So we have that the voltage outside the sphere falls off at a rate of 1 over r for any point outside the sphere. So the further you get away, the less voltage you experience. And that's the solution to part A of problem 17. Now, problem 17b, we are given a uniform surface charge all over the outside of the sphere, and we're asked to use the results of example 3.9, which gives us these two lovely equations for the voltage inside the sphere and the voltage outside the sphere. And the reason they come up with this for inside the sphere is because this b sub L term would blow up at the origin, and the reason this one doesn't have an a sub L term is because because this term would not be able to fall off as you got further and further away from the sphere, as we'd expect it to be. And then we're given these equations for the constants. And the rest of this problem is pretty much very similar to part A, because we have a constant surface charge density. So again, it comes out of the integral, just like the voltage from part A. And again, we'll apply the orthogonality conditions, and that will simplify our a sub L to 0 if L is not equal to 0, and then that integral will evaluate to 2 in the case that L equals 0. So we're just left with all these constant terms outside, and it evaluates to r sigma naught over epsilon naught. And then since we know a sub L, we can plug it back into the b sub L equation, and we'll end up with b sub L equals 0 if L is not equal to 0, because a sub L is 0. And then we'll have b sub 0 equals r squared sigma naught over epsilon naught in the case that L equals 0. So we can take these values and plug them back into the voltages we were given at the start. And so once you do this, you end up with a voltage inside the sphere, and the voltage outside again falls off at the rate of 1 over r as you increase the distance away. And that's all of problem 17. Merry Christmas, Dr. Store.